Hi, welcome to using acceleration for smoother particle simulations. My name is Ben Andersen. I'm an effects pipeline TD at Luma Pictures. The problem that we're going to solve is when we have a fast-moving emitter, we often see discontinuities between each step. The typical solution that we have is to increase the substeps. Unfortunately, this increases our simulation time. If we write those to disk, it increases our disk usage. In addition, it still only really hides the problem. If we let a simulation run for long enough, we'll see those steps emerge. So our goals are to create particle simulations that are easier to understand, that are faster because we're not going to be running simulations with substeps as often, and we're not going to be writing those substeps to disk. This approach is good for anything that's moving quickly or rotating quickly, anything where the emission velocity falls off dramatically, or just changes over time. So some examples would be sparks from a slowing grinding wheel, or the bubbles from a diver's respirator, or debris from an exploding rocket. I use this approach for all of my particle simulations, and so far so good. So to begin, do a quick review of motion blur. In film, when something is moving very quickly while the shutter is open, we're going to capture that as a streak, and in computer graphics we simulate that by taking 2 or more samples and usually linearly interpolating between those samples. There's a few different approaches that we can use to get those samples. So the first is deformation blur, where we have access to the original live geometry. So in here, in these examples, we've got this rotating object, and green is the previous frame. We're hitting yellow, it's the current frame, and red is going to be the next frame. And so if we sample that animation curve, we get this on the previous sample, and then we get a point here on the next sample, and then we can blur between them. Then with 3 samples, we're getting closer to the original curve, and then with 7 samples, we get a pretty nice representation of that animation curve. Now, one thing to notice is that the 2-sample blur doesn't actually go through the whole frame sample for something that's accelerating quickly, which is why you can see wheels actually shrink if they're rotating quickly enough, and the motion blur style is 2-sample deformation blur. So the problems that we have with deformation blur is it requires multiple frames in order to get that streak, which is not really suitable for particle work. So one step beyond that is if we've cached the samples to disk, we need a way to interpolate between those samples. So you can see even with 7 samples up here, with no interpolation we get no blur. With linear interpolation, we get basically a line from green to yellow and then yellow to red. And with cubic interpolation, we get back to a pretty nice arc, but again, same problems with needing to be able to load that geometry multiple times to get that curve. So for particles, a lot of the time we'll see velocity blur, which is where we've encoded the velocity onto the particles themselves and then extrapolate those samples before and after. So this equation here is what we use for that. So the new position is the old position plus velocity times the time sample. And so as t goes negative, we go to the previous sample, and then as t goes positive, we get close to the next one. And so we're able to reconstruct this motion blur streak without actually loading this geometry. Unfortunately, velocity blur doesn't really look very good a lot of the time, and it can be kind of confusing if you have multiple sources that kind of overlap with each other. you can end up with something that's sort of like a spider web. Can't really tell where the particles came from or where they're going. So one step beyond that is acceleration blur, and this is where we've encoded velocity and acceleration onto the points, and we can reconstruct this curve without actually loading this geometry at render time. And so this is a much nicer way to render particles a lot of the time, and it's often actually a nicer way to render regular geometry, animation geometry as well. If something is moving very quickly over a curved surface, like an eyelid blinking, a lot of the time you will have like 7 or 9 samples of the geometry written out so that you can actually get across that curved space. But with acceleration blur, you can do that with just one. So that saves disk space there as well. So it's worth noting that these 3 different arcs, although similar, they are not the same. None of these match each other. And if this is the truth, you know, we're not quite hitting that. But for our purposes, acceleration is, you know, plenty good enough. If you did want to take that a step further, you could use jerk. So this is the standard kinematic equation. This is only really valid if we have if acceleration is constant over the time interval, which would be very rare if you are emitting off of a hand animated object. It's only really true if you're emitting points and the only force that's acting on it is gravity. If you wanted to do better, you would use jerk. This is the equation for jerk. It would not be hard to use it, but I have not needed to use it, but you know, feel free if you want to. So, particle simulations. So to start, I'll just show you. This is with the defaults for pop, and you can see pretty dramatic stepping in these particles. If we change the defaults of the pop source, we can get to this, which it's definitely better, but you can obviously see that there's steps in there. It'd be hard to imagine that this kind of thing would get approved. And so this is with our approach. We have pretty nice continuous arcs here, and there's no substeps at all to achieve this. So pretty happy with this, and it works pretty well, in my experience anyway. So to begin, I'll just go over this frame range node. I use this to evaluate the math of our interpolation. I recommend that you build one yourself. So in here, yellow is the whole frame again. It started through red and goes through to green. As a bonus, you can use this setup to build a really nice regioning tool for a character's animation by setting up the frame range to be the entire scene frame range and then just putting a bounding box over it. So in order to set this up, so I've got Craig's hammerhead here, and so I'll start with the time shift here. I just added a spare parameter here, which is the beginning and the end, and then the increment. Set the frame to be the last frame, and that is because the trail node in preserve original mode will start at the current frame and then go back some number of frames at a given interval. So the number of frames that we're going to do is 1 plus the difference between the end and the start divided by the increment. That gives us 9. And set the increment to the increment on the time shift. And upstream of the trail, if you set a frame attribute, you can use that to drive color. And so it's just a nice way to evaluate whether or not we've gotten the interpolation correct. So So the approach that we're going to take for particles is to use the lessons that we learned from motion blur. So in this image, the larger spheres are the whole frame samples, and the smaller ones are the acceleration-based interpolation between them. And so you can see that we got a pretty nice smooth spiral, which is what we're going for. So the first step is to calculate the motion attributes. It's important to conceptually separate the emitter velocity from the emission velocity. This is sort of different from a lot of the way that the setups in Houdini typically work, but it's a key component to getting this to work. So if you imagine a train grinding its brakes and sparks are flying out of the side of the wheels, the velocity of the train is not the same thing as the velocity of the sparks. They may be related, but we are going to solve the attribute, the motion attributes for both of those separately. So the setup for this looks like this. So the first trail is just to get the velocity and acceleration of the position. Set this to compute velocity, central difference, velocity approximation, toggle on compute acceleration, and that's really it. Now here I've split this out into this branch here. I've got a null here. You could do anything you want to do velocity here. You could add to the existing velocity, you could completely replace it, whatever you want. I'm just going to use the input velocity for this example, but feel free to do whatever you want here. Then, because the trail doesn't take an input vector attribute, we're going to replace P with V. And this is exactly the same thing as this one. Then we're going to copy these attributes back onto the original geometry here. So V emit is the emission velocity, A emit is the emission acceleration, and J emit is the emission jerk. Those are separate from position and velocity and acceleration. Velocity in that case being the emitter velocity and acceleration being the emitter acceleration. So any manipulation to velocity needs to happen at this stage. And that is because any changes to velocity need to be reflected in the emission acceleration and the emission jerk as well. And so, yeah, any changes to velocity need to happen here, which is mildly inconvenient, but not too bad. So in order to calculate motion attributes, you do need some consistent source. If you have ID, you can use that. It's very unlikely that you would have ID on a source. And so you're sort of left with two options from there. You can use, you can calculate the motion attributes on the polygons first and then scatter, or you can use a scatter constant setup and then cull the points down that you're not using. So this is the first option. I usually use this because I don't like creating many more points than I will use. But if you did want to use a scatter constant, the way that works is that you time shift to a rest frame, scatter, point deform them back onto the animated polygons, and then you've got a consistent point here. Then you can use calculate motion attributes there. Then you could cull this down, or whatever you wanted. So to do the interpolation, we are going to separate the bias from the interpolation. And we're going to separate, the reason for that is that we want to be able to swap out the bias modes while keeping the interpolation node the same. So the bias is going to go from -1 to 1, where -1 is the previous frame, and 1 is the next frame, and 0 is going to be the current frame. So direct, it's really just for debugging. It's just a slider, and that way we can sort of scrub around and see, how things are moving, especially with that frame range node. Then with time bias, we can this is where we could scrub on the time slider, or the play bar. So the time bias ranges from -0.5 to 0.5. The reason for that is that at -0.5 and 0.5, it's actually going to swap to the next frame. So our implementation is it's really only going to support whole frame motion attribute samples. You could change this relatively easily to support more than that, but we won't cover that here. Time bias does hit floating point precision issues reasonably quickly, especially at that 0.5 bias, and that's because our int frame will round to the nearest frame differently than $f will. And sometimes, depending on what else is going on in your scene, sometimes you'll hit a floating point issue where rint will go down and $f will go up, and so you'll end up with motion attributes for the next frame, but a bias for the previous frame, or vice versa, and you end up with a really strange thing happening at the midpoint. Fortunately, you don't really need that for time bias. The range that we typically care about is -0.25 to +0.25, or negative half a shutter to positive half a shutter. So as a bonus, with time bias mode, you could actually, if your renderer doesn't support acceleration blur, you can just use this interpolation in time bias mode to add it with deformation blur. So turn off velocity blur and just render deformation blur on your interpolation node, and it will do that blending for you. Get really nice curved motion blur. So for particles, we're going to use age bias. So the ages that this expects are negative time increment to 0. So 0 is going to be the older particles, and negative time increment is going to be the younger ones. The reason for that we'll get more into in a minute, but we need that for the correct behavior. So the bias maps negative time increment to 0 and 0 to -1. And what that means is that the oldest particles are going to be at the back of the streak. So the interpolation node itself, this is the equation that we use for that. And this is the standard kinematic equation that we were looking at before. And so T is just bias here. And you can see that the acceleration component here, it's T squared, bias squared. So this little animation, when particles are added to a simulation, they are all added at once. This is going to demonstrate what would happen if those particles were born in a continuous way across that time frame. So this circle here is our emitter, and it is moving from current frame through to next frame. And this number here is the age of a particle that is born at each point here. And as this moves along, these points will age. So this is what's going to be added to our simulation over one time step. And you can see that the points that are emitted at this location have an age of 0 all the way back to a time increment, an age of the time increment. And the position on this line it's directly related to its age. And so its position on that, its birth position is it's a function of its age. So if we add the emission velocity and we see where these particles are going to go, if we set this up incorrectly, we'll get a full amount of integration applied to each of these particles. So these are all going to drop down here. And if we look at more than one frame, we can see that there's a clear discontinuity here. So the correct setup is to, a particle of 0 should really be at the emitter because it hasn't had any time to move, whereas a particle with an age of a full time increment will get a full time increment worth of movement applied to it. And that is how we get a nice continuous curve through multiple frames. And the way that we do that is with negative age. So the way that the pop solver works is if points are added with a negative age, then they get that correct behavior for the frame that they're born. So the changes to the pop source that we're going to make are we're going to set the jitter birth time to negative, and that's going to get us that nice integration behavior on the first frame. And we're going to replace all of the jitter source options with our new interpolation logic. So this is just the bias age here and our interpolate. And we've also gotten rid of the velocity manipulation nodes. As I said before, the velocity manipulation, such as adding noise or scaling it, that all needs to happen at the motion attribute calculation stage. You could add that in here as well, but we're not going to cover that right now. So the solver itself doesn't need to change. The only thing that I like to do is I like to feed it into the second input here, and that's because I want the particles that have enough age to partially move, I want them to get that partial movement on the first frame that they're born. Otherwise, they get this like weird tail on the first frame because they're just like stamped on their birth position on that interpolation curve, which it's going to be discontinuous. All right, so flip simulations. So the same approach can be used for flip because that's also based on particles. So to show you what that looks like, so this is with the standard flip setup, and you can see here that there's pretty dramatic stepping here. With flip, it resolves reasonably well because the velocities all end up blending into each other. But even here, you can see that we're getting these spikes, and if you got a note to kind of get rid of these spikes, it'd be very hard to address. And so without substeps, with our approach, we get this nice arcing flip sim, which, yeah, looks pretty good. So in order to set that up, yeah, so this is the same sort of stepping. The crux of the issue is that flip wasn't really built with age in mind, but it's pretty easy to fix it as well. So the change is, again, to get this smooth arc here. So this is inside the volume source node, and you can see that up here, this is where the positional offset is, but way down here, this is where it's setting up life, including age. So the positional offset, you can see that the position, it's basically just based on a random number, and it always jitters forward, which basically guarantees that it's going to overshoot the emitter. And then the setup life, that forces age to 0, which virtually guarantees that you're going to see stepping in your final result. So the solution is to move setup life to above our new nodes, and then replace the positional jitter with the bias age and interpolate, which is exactly the same thing that we did for the pop source. And then we're going to modify setup life to give us an age that is between negative time inc and 0 again. Now, one thing to note here is that we're going to use a different seed for age. if you look at the setup life in the pop source, it uses the same seed for age and life, and it's a little strange that there would be a relationship between how long something will live and its initial age. It's not too big of a problem, but I recommend making a different age here. So for the solver, the changes here are pretty simple. So we just want to enable age particles here. Probably want that to always be on. And then to start, we're just going to set the max substeps to 1. We'll add substep support in a minute. So this is inside the flip solver. In the overview here, you can see where we are. There's this pop solver here, which is the particle velocity input. And if you look at the pop solver, the correct order of operations is to integrate the point positions and then age the particles. Unfortunately, Flip does this backwards. And the reason for that is that when you enable age particles, it enables this on this pop solver, and also read particles will do that here. So I recommend that you break these expressions here. We still want integrate velocity to be on. And then we're just going to add another pop solver at the very end. So this is in the last step. This is pointing to where integrate particles actually is. So we want to make sure that this just happens after that. And just move the age and reap toggles to this node instead. And then lastly, I find that I get the best results if I plug into the particle velocity input here, which feeds into this to the pre-solved pop solver, for the same reasons that we want to see those particles move to get integrated on the frame that they're born, instead of getting them stamped in on their birth interpolation curve. To support substeps, it's pretty easy if we calculated the motion attributes on the whole frames. Solving it in a general way is a bit more complicated, so we won't cover that here. The approach that we're going to take is to create our streak of particles and then divide it up into slices based on the current substep that we're on. But the streak itself is going to be the streak for the whole frame. So the complications that we have with this are that in whole step simulations, we start from the whole sample and interpolate backwards with age. But with substeps, when the frame hits 0.5, we're going to jump to a different set of motion attributes. In addition to that, DOPS modifies the time increment. So that is the substep time increment, which will interfere with our ability to make that whole frame streak. So the solution for that, the solution to the first problem, is to put a time shift upstream of all of our nodes here, and just set that to the frame to be the ceiling of the floating frame. And that's going to lock us onto the whole frame sample so that we can go backwards. And this setup works exactly the same for both pop and flip. The bias offset node that we're going to add here, that's going to be choosing what our which slice that we're on. So the responsibility of this is basically to determine which substep that we're on, and then it makes an offset, and this is set to detail. And then the bias age, that's going to get this offset, and you'll notice that we're going to add the DOPS time increment, but we're dividing this by the whole frame time increment. So the whole frame time increment is sampling here, and that's written out there. And then the change to the interpolate node is to use the whole frame time increment as well. And that gives us this. So each color is a separate frame here, and each color is a substep here. And so you can see that they blend pretty nicely together here, and then this is the final result. Thank you so much for listening. Feel free to reach out if you have any questions about any of this.